let's take a look at the Pentagramma Mirificum, which is Latin for miraculous pentagram. This shape was described by John Napier in a book in 1614. A couple centuries later, Carl Friedrich Gauss studied its properties, published in a book in 1866. In 1871, Arthur Cayley published a short article on it, and in 1971, HSM Coxeter added more ideas in an article. The Pentagramma Mirificum occurs on a sphere. To make it for myself, I took the plastic globe part off of a toy like this and eventually created this. On one half of the plastic globe, I began by drawing a spherical triangle TAP with right angle A. I then held the other half of the plastic globe in place over the first half to draw a great circle that has T as its pole and another great circle that has P as its pole. I labeled the intersection of these two great circles as point R. Next, I extended the sides of triangle TAP until they met the great circles and labeled their intersections as shown here. At this point, in terms of labels, T is the pole of the great circle containing B, Q, R, and D, and P is the pole of the great circle containing C, R, S, and E. We can make a couple observations. By definition of a pole, arc TB is perpendicular to BQRD at B. Arc TD is perpendicular to BQRD at D. Arc PC is perpendicular to CRSE at C. And arc PE is perpendicular to CRSE at E, giving us right angles at B, C, D, and E. Now we can see 5 spherical right triangles around a spherical pentagon. Taken as a whole, we have the Pentagramma Mirificum, which looks like this in my physical model. I flipped it over and wrapped the flat side with saran wrap, held tightly in place with a rubber band, and marked the center. Some measures of angles and arcs, along with some other facts, are given here. We call the pentagon self-polar because each vertex is the pole of the opposite side. Napier developed trigonometry for the right spherical triangles. Gauss showed that if we let alpha, beta, gamma, delta, and epsilon be the squares of tangents of arcs as defined here, then some identities occur. If the pentagon is regular, more identities hold true involving the golden ratio. Gauss also showed that the product can be expressed a couple interesting ways through derivations like these. I got a little flashlight to shine light through the half globe that contains my model, with the dome part resting on a piece of paper and the flat saran wrapped side up facing me. I held the flashlight at a height higher than the sphere's diameter and then lowered it until the saran wrap stopped me from dropping any further. Watch the shadows on the paper as I did so. You should notice some changes that occur along the way. At some time during the lowering process, my flashlight would have been at a height equal to the sphere's diameter, at which point the shadows look a little bendy but seem to form petals of a flower. We could imagine closing in 5 petals as shown here. We can think of the flower as being the projection of the Pentagramma Mirificum from the sphere onto the paper when the flashlight is shining from the north pole of the sphere. When lowering further to the point where the flashlight rests on the saran wrap, the projection looks more like a star with straight edges and 5 points. We could say that the flashlight is shining from the center of the sphere in this position. Here is a comparison of the projection from the North Pole, or top of the sphere, against the projection from the center of the sphere. When working with the Pentagramma Mirificum, we typically work with projections from the center of the sphere. In mathematics and geography, these are called mnemonic projections and have the properties listed here. The piece of paper is called a plane, and the sphere and the plane touch each other at a point of tangency. Other than at the equator, each point on the sphere has a corresponding shadow point in the plane. Sets of points on a great circle or arc on the sphere form a line or segment in the plane. The curvy pentagram on the sphere becomes a straight-edged irregular pentagram in the plane. If we were to keep the flashlight at the center of the sphere, but tilt the sphere to a different point of tangency with the piece of paper or the plane, we would get a different straight-edged irregular pentagram due to the way the light affects the orientation of the shadows. When playing with my model, I got projected shadow images like these. In any case, inside an irregular pentagram is an irregular pentagon. The pentagon in the plane has some interesting features. Gauss said that each such pentagon can be circumscribed with an ellipse. Gauss also said that the 5 altitude lines of the pentagon will all meet at the same point, which is the point of tangency with the sphere. Cayley considered the 2 parts of each altitude line as separated by the intersection point and said that multiplying the lengths of the 2 sections of each altitude line will produce the same product. In fact, the square root of this product is the radius of the sphere from which the Pentagramma Mirificum was projected. Cayley also considered setting the pentagon in the Cartesian coordinate plane with the intersection point at the origin and said that the x and y coordinates of the vertices satisfy certain equalities as listed here. The square root of the absolute value of the result is the radius of the sphere. Suppose we are given a pentagon that supposedly comes from a mnemonic projection of the Pentagramma Mirificum as shown to the left. As shown in the middle, we could add the altitude lines and see that they do indeed all meet at a common intersection point. As shown to the right, we could then position the pentagon in the Cartesian coordinate plane with that intersection point at the origin. Suppose approximations of the coordinates of the pentagon vertices are those listed here. To find an equation of an ellipse, we first need to know the standard form of a conic equation. To make life a bit easier for ourselves, we can normalize the equation, essentially turning the unknown constant f to 1. For the normalized form of a conic equation, we still need to determine the 5 unknown coefficients a, b, c, d, and e for a particular problem. To do so, we use the x and y coordinates of each given point to write equations that the points must satisfy. 5 equations will help us find the 5 unknowns. We can represent this system of equations in a matrix and find its reduced row echelon form. Doing so produces the desired numeric values for the coefficients. For the specific given points at hand in our example, this process leads us to the decimal approximations shown here for a, b, c, d, and e, which can be inserted into the general conic form to produce the specific equation of the ellipse that contains the given points. So, in this case, we can indeed find an ellipse that circumscribes the pentagon. We could use the vertices to determine distances to and from the origin of the 2 sections of each altitude line and find their products. In this case, we arrive at the same product of 9 for each pair of sections. If we label the coordinates of the vertices as shown here, we can test the Cayley equalities. We find that all results are the same value, which is -9. Then, from either of Cayley's observations, we can say that the radius of the sphere is the square root of 9, or 3. For the following problems, see if you can determine A, whether or not the 5 altitude lines meet at a single point, B, if there is an ellipse that circumscribes the pentagon, C. Computations for the Cayley equalities, and D. What the computations tell you about the radius of the sphere from which the Pentagramma Mirificum is projected to produce the pentagon in the plane. For each problem, a set of 5 vertices is given along with pictures of the related pentagon with and without a grid. You might like to use a dynamic geometry tool like GeoGebra to explore what happens. For example, you could type in the given points, connect the points with segments to create the pentagon, add the altitude lines from each vertex to the opposite side at a right angle, and observe the result. In this case, all 5 altitude lines do meet at the same intersection point. Finding the equation of the ellipse in order to graph it around the pentagon involves solving a system of 5 equations using the 5 sets of coordinates of the vertices in the form of a conic equation. Doing so for this problem produces the approximate equation shown at the bottom of this screen. If you are familiar with conics, you might know that another way to represent an ellipse is to use major and minor axis information in a geometric form of a conic equation, which leads to the form shown at the bottom right for this problem. Testing the Cayley equalities should produce -1 for each computation. The square root of the absolute value of this result is the radius of the sphere. Here are 3 more problems to try. You can compare your results for number 2 to those shown here, for number 3 to those shown here, and for number 4 to those shown here. Hopefully you learned some things about the Pentagramma Mirificum on the sphere and its mnemonic projections in the plane.